Welcome to the Basic Mathematical Intuition for Robotics webinar. This is the first course being conducted by PES University's IEEE RAS student chapter. This course is going to be a basic intuition. It's just going to be a start so that students who are interested in robotics can understand the different mathematical concepts which are going to be used while they're actually modeling their robots, whether it's mathematically or actually building a robot. So this course might not completely go in detail to the mathematics and the methods of solving real life problems. So for that, we have made another course which will be coming up shortly right after this course, which will go into the detailed math. We right now have 55 people on the live stream. Hopefully everyone can hear me. There is a live chat, so everyone can post on their live chat as and when they feel like, if they have any questions. We might not address them directly. We will try to keep this session within 1 hour, and we will address as many questions as we can nearby the end of the session. So if everyone can hear me, just send in a message on the chat, and then without any further ado, we will get into the sessions. Okay, also we'd like to just bring to your notice that all of these sessions, we will try our best to have them available on YouTube itself for further reference in case anybody wants to. But in case we do not successfully do that, we would recommend that everybody does attend these live. And yeah, so we'll get into the session right now. So the first thing that we do is figure out how robots are to be classified. Normally, if you were to go with the conventional categorization of robots, they could be categorized based on so many different things, whether it's the type of sensors that they're using, or what type of algorithms they're using, etc., or their form factor, as in the shape of the robot and things like that. So they could be pre-programmed robots, which mostly industrial robots would use for their assembly line and stuff, where they don't really sense anything. They just have a pre-programmed set of instructions that they keep repeating on a regular basis. Or they could be based on their form factor, such as a humanoid robot, such as this. And recently, humanoid robotics has become a huge thing, and everybody's going into humanoid robotics. The next thing is autonomous robots. That's another category of robots altogether, where they have sensors and they might use different algorithms to make decisions as to what should happen. In fact, one of the simplest autonomous robots are line following robots. And just like that, you could categorize robots in multiple different ways. But when it comes to actual mathematics for modeling a robot, there's one major aspect that we actually use to categorize robots. That are the joints. We use what the type of joints are and how many joints there are to categorize robots when you're trying to model them mathematically. So there are two major types of joints, again, for mathematical categorization. One is called the revolute joint, and the other one is called the prismatic joint. So just to give you guys an idea of the revolute joint and the prismatic joint, we will take a look at these. So here I have two joints. One is a revolute joint and one is a prismatic joint. So first, to look at how the revolute joint would move would be like this. They move about an axis. So hopefully you guys can see how the rotation of a revolute joint happens, and it generally happens about one particular axis for a single joint, although you do get different joints where you get types of joints where you can have multiple axes of rotation. But in the simplest case, a revolute joint is a joint which moves about an axis. If you were to look at it from a different perspective, this is how it would rotate. Or in fact, it could be about a different axis altogether, such as this movement. This would also be a revolute joint. The other type of joint that we spoke about was a prismatic joint. Now, a prismatic joint is one that moves along an axis. No more about an axis, but along an axis. So, for example, this one would move in and out. So this is a prismatic joint. There are multiple ways by which we can achieve prismatic movement, but all that aside, a prismatic joint would just have basic movements like that. So once we know that these are the two types of joints, we can start actually categorizing robots based on these joints that are present. So the types of robots when it comes to joints for mathematical categorization, the first, the simplest, would be a planar robot. So to demonstrate a planar robot, before we get into planar robots, I'd like to show you guys what would happen if we had just a single joint. So this is a single joint, and if we were to rotate it, you could see that the end effector, the endmost point where we actually have the tool which would be used to either pick something or drill or spray paint or whatever be the objective of the robot, that end point is called the end effector. So this end effector can only move about one single circle. We can't reach any of the places in between. If we had a top view of the robot and we wanted to reach, let's say, this point where this cursor is, if we were to try and reach it, we wouldn't be able to. We'd cross over it. So the first thing to be able to reach, so this would actually not be that helpful. You'd go only about a circle. And similarly, if you had a prismatic joint, such as the one we just showed, you would only be able to reach the points on this line. We wouldn't be able to reach anywhere outside that. So we come to planar robots. Planar robots have two joints. They could be both rotational or they could be both prismatic, and in fact they could be one prismatic joint and one rotational joint. But the cool thing is that when one of them rotates, the other one follows, and this joint would be independent of the first joint. So just with this much, we would be able to reach any point we want. For example, if we wanted to reach, let's say, this point where the 3D cursor is, all we'd have to do is first move this joint by approximately this much, and then this joint down, and there we could reach this point. The end effector was able to pick up this point. So this, we would actually be able to reach any point on a given plane. Of course, that does depend on a lot of things, such as the lengths of these links. The official term is links, but basically these lengths are what decide how much of the two-dimensional plane can this robot actually reach. And that area that we can reach, we term as the workspace. So you can imagine if this link was slightly shorter, then obviously we wouldn't be able to reach a point very close. The link would not be able to reach it. So we'd actually have like a disk with a central hole cut out. In fact, we do have that right here. If we ever tried to reach this exact central point, we wouldn't be able to reach it, no matter what we did. So yeah, but apart from those few points, we are able to reach most of the points in a two-dimensional space. And as all of you would recall, this is something similar to polar coordinates. Similarly, if we were to go into Cartesian coordinates, we'd have two prismatic joints. So for example, we want to reach, let's go into a top view, or before we go into the top view, just to explain how this robot would work, we'd have this thing, which could move as a prismatic joint along this particular link. So it would move like that. And we can stop it wherever we want. And this one, let's say this was a sphere with gears on it, while by rotating this, we would be able to move this again, front and back. So if we wanted to reach any point on this two-dimensional sphere, we'd be able to reach it. For example, if we wanted to reach this point over there, we'd simply have to move this like that, and then move this forward, and we'd be able to reach the point. But a huge disadvantage of these kinds of robots is that we can't reach all points in 3D space. If by chance the point was just above over here, no matter what you did, you would not be able to reach this point. So these planar robots stay to a plane. They can't use a third dimension. So to fix that problem, we have the next kind of robots, which are the Cartesian robots. Cartesian robots use Cartesian coordinates, so they have 3 prismatic joints. And with this setup, of course, they could be in any order. We could reach potentially any 3-dimensional point. For example, this one would move in a very similar manner to the previous one, where we'd have one that moves like this, followed by this itself that moves like this, and we'd have a third link. Because of this joint, we'd have another joint which allows us to move this third link up and down. So in this sort of a robot, we would actually be able to reach any point in 3D space, given that that point lies within its workspace. For example, if we wanted to reach this point right here, we would be able to reach that point by first moving this back, moving this down, moving this to just underneath the point. Hopefully that's just underneath. Moving this back out, and then moving this slightly up, and we'd be able to reach the point. So that's the good thing about these points. Oh, I slightly missed, but that's all right. We'd get into that later on. So that's the good thing about this Cartesian robot. We can reach any point in 3-dimensional space within the workspace. So its workspace is actually in 3 dimensions. Of course, in this particular case, we'd always reach the point from the bottom, but that can be easily fixed by just changing which direction the movement occurs first. Now, the next type of robot that we have is spherical. As you guys could have guessed from 3D geometry that everyone has been doing from, I think, 11th or 12th standard. There are Cartesian coordinates, spherical coordinates, and cylindrical coordinates. So obviously we'd have robots of each of these types. So the Cartesian coordinate, as you know, forms a cube. So the workspace would be in the form of a cube. You'd reach every point in a cube. The spherical robots, as we know, spherical coordinates were made out of three different variables, which was theta, phi, and rho, or r. So just by theta, phi, and r, we were able to do it. So theta and phi were two angles, so we'd require two angular joints, so two revolute joints, and we'd require one prismatic joint for r. And that's exactly what this kind of a robot has. This kind of a robot has one joint, which is a revolute joint, which would give you the value of theta. So you can rotate this to get a value of theta, after which you would have to rotate this to give you a value of phi. So this mechanism, you can reach whatever phi value there is. And finally, with another prismatic joint, you would be able to reach the value of r, whatever be given. So this spherical robot would actually have a sphere as its workspace, and it would be able to reach any point in a three-dimensional sphere. So that is how these robots would reach any point whatsoever. And since we said Cartesian spherical, the last type has to be cylindrical. So cylindrical robots can reach any point in a cylinder. It would have a cylindrical workspace, and cylindrical coordinates, if everyone can recall, they consist of one value of an angle, theta, then it also consists of a rho, which is similar to r, and then it consists of a height. So these cylindrical robots have the exact same concept. They have one revolute joint, which can give them a value of theta, just like this. Then it would have one value that decides the rho, which would be, let's say, this joint. Where it can move to give the value of r or rho. And then finally, this joint, which would give it the height. So just with these three joints, again, it can reach any point in three-dimensional space and in a cylindrical workspace. And that are the three main types of robots. But what would happen if you start adding in joints? There's no reason why I wouldn't be able to add yet another joint to this and create a more complicated robot. So that's why they've generalized all of these robots into a different method of naming the robots. So that is the generalized version, where we name them based on the types of joint and how many there are. So a planar robot would be called either 2P, 2R, or 1R, 1P, which means there would be two prismatic joints, or else two revolute joints, or else one rotational and one prismatic. On the other hand, a 3P would be Cartesian. It would have three prismatic joints. So three prismatic joints would be like your x, y, and z values. Spherical would be 2R, 1P, two revolute joints and one prismatic joint. Cylindrical, on the other hand, would be two prismatic and one revolute. Similarly, you could have any form of robot, which could be 3P, 3R, 2P, 3R, 1P, 4R, and so on and so forth. They would keep going on simply depending on the number of joints that you have. So an example of a robot that doesn't fall in these three categories and has more degrees of freedom would be this particular robot over here. It would be a pick and place robot. We've designed this for one of our future classes. We will get into a bit more detail of this robot, but for now we have one revolute joint which allows it to rotate, and then we have another revolute joint, then we have a third revolute joint, and then we have one prismatic joint. So this would actually be a 3R 1P, and we will get a bit more into details of this particular robot a bit later in the future classes. But yeah, so these were the types of robots, the way robots are categorized for mathematical intuition. But apart from mathematical intuition of these robots, how do we actually go about the math? Till now, I only showed you types of robots, but we still haven't gotten into anything mathematical, or there's no reason as to why we would think that mathematics is needed. Here we just decided different types of robots, but we haven't gone into any math. So before we get into the math, there are a few concepts that you need to understand, which is what we will go through in the next 15 to 20 minutes. And how those are actually applied is what we will go through in the next few classes and in more detail in the second course that will be coming up. So we come into what the concept of frames are. We have to understand how points in 3D space are represented for robotics. So we come into frames. These are the coordinate axes. Of course, we follow a right-hand rule, so while going from x to y, you should point in the positive z direction. So that's why this is the negative x. Positive x would be in this direction. But for demonstration purposes, I've shown only the negative x axis. And you could have points with coordinates that are basically the perpendicular distances of the point's shadow to these axes. So in fact, this point should in fact be -3, 2, 2. It's an arbitrary point that I've taken. It's not necessarily actually that. But yeah, this point is at 3, 2, 2 with respect to this frame. But what we actually don't realize, I'll just take a random example from here. These are all stored for later uses. For example, we have this robot. This, as we know, is a cylindrical robot. Let's say we know where this point is with respect to this universal base frame that we have. We know that, okay, it's at 3, 2, 2. But while programming this robot has to have its end effector go to this particular point. Now we only know where this point is, what this point is with respect to this frame. We have no idea what it is with respect to this new frame that we have. So we really need to figure out how we can find out what these points are with different frames. And the fact that this has multiple joints, we need to know where this point is with respect to this end effector, with respect to this joint, with respect to this joint, and all of those different things. We'll get into exactly why and all of that in a future class, but for now we are only trying to find out how we can represent that. So we will move this back down and concentrate just on this frame. So there are actually two things that can happen to a frame. The first thing that can happen is it can actually move. So this could be another frame with respect to this point. And another thing that could happen is that the frame could have been rotated. So maybe this is let's say the orientation of the end effector. This is the new frame, and we have to find out what this point is with respect to this frame. So this entire movement can actually be made into two things, which was one was a rotation and one was a translation, a movement. So that's exactly what we need to figure out. How do we find out what this point is with respect to this new frame when we only know what it is with respect to this frame? So we're going to get to that, and we're going to split it out into two things. The first thing is going to be translation, which is just moving the frame without any type of rotation. That would mean that this frame will be parallel to this frame. Every single axis will be parallel from all directions. In this case, how do we find out what the value of this point is? So that goes into the translation of a frame. Now we can do this very mathematically using something called matrices. Hopefully everyone has studied matrices. I think it's there in syllabus right from 10th. So we generally represent a point as a vertical vector. We show it as a column matrix. But since I couldn't make column matrices over here, I just used a transpose. And everybody knows what transpose does, so we know what this point is. So we represent a point with the letter P, and this superscript A says this point is 2, 3, 5 with respect to frame A. So in our example, if we were to represent this point and we just say minus 3, 2, 2, we don't know if this minus 3, 2, 2 is with respect to this frame or this frame. We can call this frame as A and this frame as B. So, or as we've actually given in our example, we've labeled this frame to be B, which is our new frame, and this frame to be A, which is our old original frame. So we know this with respect to this, and we have to figure out what is this point with respect to this new frame B. So according to our translation of a frame formula, the first thing that we need to know is the point of origin of frame A with respect to frame B. I've taken arbitrary examples, so don't look into that too much with the example that I'm giving on Blender. This software is Blender, it's 3D software, just to give you guys an idea of all of the points. Yeah. So how we are going to be going about it is, the first thing that they said is we require the origin of frame A with respect to frame B. So that means this is our frame B. We need to know what is this position, the origin of frame A. In frame A, the origin is 0, 0, 0. But what is this origin with respect to this new frame? So if we assume that this origin, in this particular case, it would be some value positive x, because this is the negative x direction. So it would be some value of a positive x, slightly positive y and a negative z. So that would be the value of this particular point. So we have to know what that point is. What is this origin with respect to the frame that we're trying to find? So once we find out what that is, the point with respect to that new frame is simply the summation of the old point with the new point. That's it. It's as simple as that. So in this particular case, as we can see, this is minus 3 comma 2 comma 2 with respect to this frame. This frame we said was, for example, minus some value of positive x, so maybe 2, some value of negative y, or we'll just assume that it's at the same value of y. So it's because it's at the same thing, we'll just assume it's at the same value of y, so that won't change. And z, let's say it's at minus 3. So this point with respect to this new frame would simply be minus 3 plus 2, so it would be minus 1, and 2 because it's the exact same on the y, and it would be if this was minus 1, so probably 1. So that would be the new thing. The new point with respect to this frame would have been minus 1, 2, and 1, assuming that this frame over here is actually at minus 2 comma 0 comma minus 1 with respect to that new frame. Hopefully that made a lot of sense, and that's how you find it out if it was a translation, only a movement where everything remains parallel. But what would happen if that was not the case? Get rid of this. If that was not the case and our frame was only rotated, there are a few types of rotations that could happen. That would be rotation about x-axis. Let's say it was rotated about x-axis by just 30 degrees. Would the value of these points change? And the answer, which should be obvious, is yes. The values would change immensely with respect to the new frame. The position would not be the same. The y and the z values would definitely change. So really the question is, how do we find out what the new value is with respect to this new tilted frame when we rotated it just about the x-axis? The similar thing could happen. We could rotate it about the y-axis by 30 degrees. So this is the y-axis, so we could rotate it by 30 degrees. And that would again change the value. Now you can see the value of x should be something. The value of z would become almost 0. So another type of rotation that could have happened is rotation about the z-axis by some degrees. I've rotated it by 30 again. You can see that the values are clearly changing, and we have to find out what it is. So to do this, again, we're going to use the concept of matrices. Now, why were we representing these points as matrices? The addition doesn't really require matrices, but what does is this rotation. For that, we have rotational matrices. So if we were to rotate the frame about the x-axis by some angle theta, we would have to multiply that point. So in our case, in our example, it was 3 comma 2 comma 2. we would multiply that 3 comma 2 comma 2, we'd put that up as a matrix over here and multiply this 3 comma 3 matrix, 3 bar 3 3 by 3 matrix with that 3 by 1 matrix, and we'd get a 3 by 1 matrix as an output, which would be the position of the point with respect to the original, with respect to that new frame. So that is what these three matrices do, are x, y, and z. And the last concept that we need to understand is, what if a lot of these are happening together? If we have more than one thing happening together, in that case, we can't just use this. We have to find out how we have to apply them. So first thing that we will do is, let's assume that there's no translation happening, but there are multiple rotations happening. So the first type of rotation we could do easily about, let's say, the x-axis, 30 degrees. And the second rotation, we will rotate about the y-axis. But here there's a small issue. There's a slight dilemma that comes in. When we say rotation about y-axis, are we rotating it about this new rotated y-axis, or are we rotating it about the original y-axis from our base frame? So there we come into another concept itself, which is the concept of moving frames and fixed frames. So if we were to rotate it, if we were to say that there's a rotation about x-axis followed by a rotation about y-axis, if the y-axis that we are talking about is this new y-axis, it would be called rotation about moving frames. You're doing the next transformation to the frame about the new changed frame. So that would be, in this case, just like this. And then maybe we could have, that was 45 degrees about the new y-axis. And then we could have a rotation about the z-axis by, let's say, 60 degrees. And that would be how the new frame turns out to be. And we have to find out what this point is with respect to that. And this, how we go about this, should be intuitive. There shouldn't be too much of an issue with understanding how we go about it, which would simply be, if we are going about the moving frames, we go through x by an angle alpha. I've represented alpha with A, y by an angle beta, B, and z-axis by an angle gamma, G. The new point would simply be rotation about x. Our x alpha actually represents the rotational matrix that we saw in the previous slide, the entire rotational matrix. This matrix, where theta in this case would be A for alpha, which is the amount by which it has been rotated. And then we'd pre-multiply that by Ry of beta. Why we're doing that Ry of beta is because, why it's being pre-multiplied is because obviously when we did rotate it about x, we pre-multiplied it with the point. The point was post-multiplied to the rotation. So if we are having another rotation, that rotation should be pre-multiplied. This gives us the new point, and that new point is being multiplied by the next rotation, which gives us a new point, which is being pre-multiplied by the next rotation. So that intuitively makes sense as to how we would go about to find the rotation about all three axes. But what happens if the rotation is about the original axes? So if it was about the original axes, the old frames, it's called rotation about the stationary frame. And rotation about the stationary frame would go like this. We would have rotation about about x-axis, by 30 degrees. We'd have a rotation about the y-axis Now you can see the y-axis is the original y-axis that we're rotating about, 45 degrees, and the rotation about the original z-axis by 60 degrees. This is not the same as what we just saw, and just to prove that, I will show you what we did previously. We were in local transformations, and we did rotation about the x-axis by 30 degrees. We did a rotation about the y-axis by 45 degrees, and then rotation about the z-axis. All of these are the new z-axis that we're rotating about. So rotation about the z-axis by 60 degrees. And clearly you can see the matrices are not aligned. They are clearly different. So the order in which, whether we are rotating about the fixed frames or the moving frames, does play a huge role. And that's why we have to know how this is happening. So we already went about the fact that when we are doing moving frames, it's pre-multiplication of the exact order in which you're doing it. So we're going first x by alpha, then y by beta, then z by gamma. So the way you would have to write that is r alpha, the r about x alpha, pre-multiplied by r y beta, pre-multiplied by r z gamma. But what happens if we have it about the fixed frame? In a fixed frame, if we are going about alpha, beta, and gamma, again, x, y, and z, the new point would actually be just the same point multiplied in the exact opposite order. So this, we'd actually have to find a single rotational matrix by multiplying rx alpha into ry beta into rz gamma, and then multiplying that by the new point. That's how we go about doing it in the fixed frame. Now this doesn't come out too intuitively, and there's a lot of math that proves why this works. But just for this particular session, we will try to prove it physically using this particular software. So first, we'll go about rotating it in the global frame in the same way. Rx will go with 30 degrees, so alpha is 30. Ry, the original frame, as you can see, we're going about the fixed axis, not the new axis, 45 degrees. And then Rz by 60 degrees. This gives us this axis. Now we're going to change into the moving frames, and let's see exactly how this works. We're going to rotate of course, from here we can see that because this is just the exact reverse order, the point should be the exact same if we were to go in the reverse order while going about the fixed frames. So if we were to rotate about z first, then y, and then x, it should come out to be the exact same. So that's why what we'll do right now is we've rotated about x, y, and z about the fixed frame, and for the moving frame we're going to do the exact same angles, except we're going to go z, y, and then x, and that should give us the exact same. It should come out as z here, pre-multiplied by y, pre-multiplied by x, which should be the same. So our frames should align. So that's exactly what we're going to do here. So we're going to take this in local. We're going to first rotate about z by 60 degrees. Then we're going to rotate about y by 45 degrees. And then we're going to rotate about x by 30 degrees. And as you can see, the frames have perfectly aligned, which means our hypothesis of having these frames written out by moving about the fixed frame as the reverse multiplication, which is actually post multiplication of all of these to find the rotational matrix, is correct, and it works out. So that was the rotation of frames. But what happens when we have both of them? Currently, I have not done that. But when we have both of them together, we are going to have to find out something called the transformation matrix. And that is actually what most of next session, which is tomorrow's session, is going to be about. Finding out the transformation matrix and something called forward kinematics and inverse kinematics and the DH parameters. So tomorrow's 1 hour, we will only talk about that and find out more about all of these things. But in general, rotation and translation can happen, and we would have to figure out what this new point is with respect to this new frame when there's both a translation and a rotation. Why we need to find that out is obvious, because if you were just to take any robot and let's take this one because it's already aligned. If you were to take any robot and look at it, the new frame is obviously going to be translated, and it's also going to be rotated at some angle to the original frame. And that's why it is needed to know what it is for both of those put together. And we will get to what that is and all of that in the next session. So till then, since we do have 12 minutes remaining for this session, I will go through a few of the doubts, if any has come up in the comments. Okay, so no one has put any comments yet, any questions. Everyone, I will be waiting for another 12 minutes to have any questions, any doubts regarding either this session or the future sessions that are coming up. Anything at all, we will be addressing all of them right now. Also, if you have any feedback, do mention all of that right now so that the future sessions, the next session that's coming up and all of that, we can implement all of those feedback, and we can make the sessions better so that all of you understand better and you can make the most out of these sessions that's happening. Okay, so we have one question from Gokul Raj asking if we will be using ROS for manipulation. No, for this session we are not actually going into any of the coding for this course, and in fact the next course as well we will not get into any of the coding or ROS. Although RAS itself is planning on maybe hosting a webinar for ROS. ROS isn't something that can happen in just a few hours, so we might have a one-day course on that in the future. We're still looking. We are contacting people from the industry to check if they will be able to spare some time to have a session on ROS. There are a lot of questions based on the software that I'm using. Yeah, it's Blender 3D. It's an open source software. It's generally used for 3D modeling, designing, and animations, CGI, game. It's also a gaming engine. It's a pretty powerful software. If you guys want an entire tutorial, a session on Blender 3D itself, just to find out how 3D modeling works, how manipulation in 3D works, you can let us know, and we will try our best to have a session solely on Blender as well. G. Dilip Raj wants to know if we'll be using ROS. No, as I've said, for this session we will not be using ROS. We are only going through the mathematics that generally people do not realize while coding for a robot. For example, if we were to have this previous robot that I had shown, we have the points over there. Now, for us as humans, it's very easy to, okay, test out the, it is very easy for us to just try out different angles and everything to get to the point. But as a robot that's using computer vision, it might find out where the point is. But the real question is, can it figure out how it's going to actually, what angle? This motor has to move by some angle, and we have to figure out what that angle is for it to actually work. What is this distance that it needs to move? What is the angle by which this base has to rotate? Those angles often people really just overlook. We have had quite a few uh, sessions. We've had quite a few competitions on robotics from RAS. We've had an ideathon recently. Before that, we also had something related to for the entrance to our mini projects to get into the RAS student chapter. For all of our major and mini projects, we had a few robotics questions put out. A lot of people spoke about the sensors that they'll be using. They spoke about the different algorithms, AI, ML, will use computer vision, but not a single person actually spoke about the different ways they'll go about actually picking and placing a robot. A lot more goes into a robot. Most people will say, okay, so we have computer vision that decides this, and then boom, we're done. We've picked it up, we've placed it, and it's over. But that does not work when it comes to real life. You have to actually mathematically calculate the angles, and you have to go about it in a correct method so that the computation time of your microcontroller does not increase, and a lot of things. I have a question saying, is Blender similar to Gazebo? In certain ways, yes. In most ways, no. Yeah, Gazebo is in 3D and all of that, but Gazebo is actually much more focused on simulations and things like that. Blender, although you can use Blender for simulations and a lot of those, Blender is not solely made for that purpose. So doing that on Blender would require much more work and a lot of add-ons and a lot of other things to be added in. Whereas Gazebo, it's meant for it. It's more for simulations. Why we're using Blender in this case is because since here we're not actually doing real simulations, I just want it to be a 3D space for you to show all of the different possible ways by which these robots can move and all of that. I thought that this would be an easier mechanism to traverse through the 3D space, and it happens much faster than Gazebo, and it would require lesser amount of coding and all of those stuff. So yeah, we have a question saying, so the coordinate calculations are done for navigation of a point by the robot. Yes, that is almost completely correct. We have to figure out all of these coordinate calculations just so that our robot can actually navigate its end effector, its tool, whatever it's using, whether it's gripper to pick up something or a drill or any of that. It has to make sure that it's putting that in the right position, and to do that it has to calculate all of the angles. It has to calculate a lot. There are a lot of other things that go in. We'll get to them as we go according to the different sessions. There are a lot of considerations that have to be made for the force, for the torque, for the velocities, things like that. It has to undergo all of those. It has to calculate for all of that to actually get the accurate position, which does not generally happen just by telling the robot, yeah, you have to go to this point. The robot's not going to be doing that. So yeah. In today's session, hopefully the takeaway for the session was to find out what categorizes different robots, which is based on the joints, the number of joints, and the types of joints, which basically is prismatic or revolute. The second takeaway should be how it's actually named, your 1R, 1P, 2R 2P, 3R 1P, etc., and what all of those mean, and how these joints actually work in three-dimensional space. How Cartesian robots work, how spherical robots work, how cylindrical robots work. Of course, those were only three examples that I've taken up. There are multiple more that have different names. There are a lot of things that we will not be going into this session, into this specific first course as well. We will be going into a lot more detail in the next following course, which starts next week, in fact. That is, the name of the course is Practical Mathematics for Robotic Applications. But for that course, because it's in more detail of this particular course falls as a prerequisite for that course. We will try our best to have this up on YouTube so that anybody who missed out this particular course can also watch this, so that they don't feel lost if they want to join the second course only. The second course will be much more mathematical. We will actually solve problems, and yeah, you will have other speakers as well for those sessions. Apart from that, all of these sessions will be held every day itself, from Monday to Friday for this week. 5 sessions. I hope all of you have seen what each session consists of, and they will be from 4:30 to 5:30. Any questions, if you are not asking them in this live chat, you can send them as a direct message to PhysiFacts on Instagram, or you can also send it to IEEE RAS PESU. Those are the two Instagram pages that will be answering all of your queries related to these particular sessions. We suggest you go to PhysiFacts, because then I will directly be able to answer your questions. And yeah, any other questions, anything else? There's 1 minute remaining and we will close for today's session. Tomorrow's session, all other sessions will be emailed again to you. The links will be emailed. We will try our best to use YouTube Live itself. And if you want any of your friends to join in, go ahead and send them the invites as well to watch the live sessions. Okay, so I guess there's no other questions, and that would be the end of session 1. Thank you all for joining. Okay, we have a question saying, can we get the PPT? Whether we'll be giving the PPT or not, we'll see. We will try our best to email the PPTs maybe at the end of the entire course. Whatever PPTs are there, we will email them. But most of the actual understanding isn't happening from the PPTs. They're more of the Blender and the 3D views and all of that, which can't really be sent. So you just have to rewatch this video on YouTube. But yeah, we will try our best to maybe email a session, email all of the PPTs as well if multiple people want it. So yeah, that's it. Time up for today. All other questions you can